All right, welcome. So in this video, I want to continue looking at Turing machine state diagrams, but I want to look now at a language or languages that are not context-free, so showing that Turing machines are indeed more powerful than a context-free grammar or PDA. What we can see here is we have three blocks that need to be held in unison, and we could use the pumping lemma for context-free languages to show that this is not context-free, and I'll leave that as an exercise. Instead, I want to build a Turing machine that's going to solve this or decide this language for me. Now I'm going to just start with an example string here, 001122. Here's my idea. Here's at least the idea I want to borrow from our last video. When we had just zeros and ones, we said, okay, cross off a 0, cross off a 1, cross off a 0, cross off a 1. Okay, but now we have 2's in the mix as well. So what do we do in that case? Okay, cross off a 0, cross off a 1, cross off a 2, go back, cross off a 0, cross off a 1, cross off a 2. That's the strategy that I want to follow. The thing that we're going to notice here is we're going to have to be crossing off stuff that's in the middle of our string potentially. And in our last example, when we had just zeros and ones, we had this idea that if we went from the outside in, we could literally replace them with blanks, and we would just get a shorter string of the same length. That's not going to work for us anymore. So blanks is probably not the right idea. I'm going to use X's instead as my symbol. When I cross something off, I'm going to replace it with an X. So let's get started. I'm in this state here, my start state. Where should I expect myself to be? I should be scanning this first 0, assuming it's there. I am going to say, what happens if we are scanning something else? Well, if we are scanning a 1 or a 2, we know that the zeros are not there, or at least we're out of order or something's wrong. We should reject. So I'm not going to deal with those transitions. Remember, rejecting transitions, we just assume all the missing ones reject. However, if I am scanning a space, a blank, then that means there's 0 zeros, 0 ones, and 0 twos, and that's exactly a case when I should accept. So I am going to say, if I'm scanning a blank, replace it with a blank. It doesn't matter what I replace it with or what direction I move, because I'm going to go to the accept state, which is where we halt and accept. So I know it doesn't matter because after this we don't do anything. Okay, then that means let's worry about what happens when we see a 0. And I said when I see a 0, I want to cross it off, so I'm going to make it an X, and I'm going to move to the right. Okay, so now we've crossed off that first one. We've turned it into an X technically, and we've moved to the right. Now what do we want to do? Well, we want to keep going until we see a 1. So I want to move to the right. I want to skip any zeros I see in this block of zeros and move to the right. I'm going to think ahead a little bit. After I find my 1, I'm going to cross it off. And to find the next one here, I might have to also skip some X's that I've already written on the tape. So I'm going to keep that in mind. I might have to put that in a few other places. I'll mention that as I get there. But that's thinking ahead a little bit. So I'm going to skip all the zeros. But if I see a 1, that's the one I'm looking for. And what am I going to do with it? I'm going to scratch it off. I'm going to turn it into an X, and I'm going to move to the right. So I'm going to keep going and keep moving to the right because we still have the 2's we need to do. So now I'm going to do the same thing as for the 1's. If I see a 1, I'm going to move to the right. If I see an X, I'm going to move to the right. But if I see a 2, I'm going to cross it off and move to the left, because in this case I've now crossed it off, and there might be some more 2's there, but if not, I'm not worried about them. I want to move to the left here and get started on my next loop. So I'm going to go here. Now that I've moved to the left, I'm going to say, okay, I need to move back to the left, cross off some X's. Let's go back to the left. I'm going to have to skip over any zeros I see to move all the way to the left. I'll have to skip over the 1's, but there might also be a bunch of X's over there. Now there shouldn't be any 2's over there because this was the first 2 I saw. And if I had seen any 2's on my way over here, I would have rejected. So there shouldn't be any 2's over there. So I'm going to keep going all the way back to the left. I'm going to keep skipping x's too, so what I'm likely going to do is run into an empty space, and that's going to tell me that I ran off the end of the left-hand side of my string, and I should move right again. So I'll move right again. Now that should have me scanning the first 0, but wait a second, we crossed off the first 0. It's an x. And I don't have an exiting transitioning here for an x, so I should think about this for a second. Right now, since there's no exiting transition, it will cause me to reject. I don't think that's the right thing to do. X is in fact what I want to do is I want to move to the right here until I see the first 0. I want to get myself repositioned on that first 0. So I'm going to use this first start state that says move to the right, as you scan x's, and then hopefully you'll find your next 0 that you need to cross off, and you can do this again. Cross off the 0, then go cross off the 1, then go cross off the 2, and then go back to the beginning. Then go cross off a 0, and then cross off the 1, cross off the 2, and then go back to the beginning. And if we do that over and over again, and let's imagine there is an equal number of x's, zeros, ones, and 2's, then on that last pass, so again, let's try with our 0, 0, 1, 1, 2, 2, we'd go x, 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 all the way back, x, 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 all the way back, and then this state here is going to skip over all the x's and go to the right and eventually hit this bucket and accept for us, which is exactly what we want it to do. So we've now added an extra step in here where I can cross off the 2's as well, and I've shown that this language, not context-free, what is it? Well, we haven't defined this yet, but we could call this Turing decidable. We've created a Turing machine that can decide or recognizes another possibility here, this language L, showing that Turing machines also are more powerful than context-free grammars or push-down automata. Okay, so that was a little bit more complicated than the ones we had looked at earlier, but not too much. We still managed to get it done with 5 states, which is good. Now I want to look at one that definitely looks a little bit more challenging. This is just going to be a block of zeros, but the number of zeros is a power of 2. So maybe 1 or 2 or 4 or 8. We need to be able to recognize this pattern, this sequence of numbers, to be able to determine if our string is in our language or not. So again, I'm going to be making a Turing machine for it, but I do want to be thinking a little bit about how we might do this if we had a big long string of zeros. Now, I just kind of wrote down some zeros. You can count them yourself and spoil it, but one way we can check to see if this is going to be a power of 2 is, well, let's remember a power of 2. One of the important things about a power of 2 is if I divide it by 2, I'm going to get another power of 2, and that's what a power of 2 means, right? I can divide it again, and I can get another power of 2, and so on. So how do I divide by 2 if I've got a unary string like this? Unary, what do I mean by that? Well, we like to think about binary or base 10, but unary is base 1, and that's what we have here, only zeros. And how do we know how big a number is? Okay, this is 7. I went and spoiled it myself. It's 7. So this is 7 in unary. Okay, now I want to divide by 2. How do I divide by 2? Well, I have to get rid of half of the numbers there. That's how you divide by 2 in unary. How can we do that with a Turing machine? We might think, hey, I could cross off the first half. That's harder to do than what we can do with a Turing machine. Instead, what I can do is cross off every other one. And if in this case, I didn't have a pair for me at the end, telling me that I must have been an odd, but I guess I've just added that pair, so now I'm an even. Again, I can go back to the beginning and cross off, not this one, every other one. Again, go back to the beginning, cross off, not this one. If you're left with exactly 1 at the end, because that's the beginning here, we went from here to here to here to here, then you know you've got a power of 2. You had a power of 2 if you can do this every time you get to the bottom. So that's what I want to try and do. I want to cross off every other one, I should say, of my symbols. Now I crossed first and then the last one I was left over was on the end. I'm going to do that slightly differently. So again, I'm going to skip 1, cross 1, skip 1, cross 1, go back to the beginning, skip 1, cross 1. That way the one that we would want would be the first one there. So let's see here. So the first one, let's just follow along for a second. If I have a 0, I said that's a skip one. So I'm going to do nothing to it and move to the right. I'm going to be, well, I'm going to think ahead. At some point I need to accept, and I'm not sure. I think it might be from this state, but let's keep the pattern going. The one that, so I said on this one though, if I see a 0 here, I should cross it off. If I see another 0, skip it, and I see that I'm sort of getting myself into this long pattern. I can do this forever, and I don't want to do this forever. I want to loop back at some point. And it's actually here that I want to loop back, and we'll see that why in a little bit further, why we didn't loop back earlier. But here, once I see this 0, when I loop back, I am going to be crossing off. And now we can see with these two loops, as long as I'm seeing zeros, I'm going to cross off every other one. Now let's be careful here. Over here I was at the beginning. I've crossed off 1, I've crossed off 2, I've crossed off 3, I've crossed off 4, 5, 6. So this state over here is the odd number state, and this state here is the even number state. And that's important for us to remember, because if at the end of this crossing off we're in the odd state and we have no more zeros, then we know we're in trouble. That means we don't have a power of 2 and we should reject. So I'm going to just keep that in mind. I'm not going to add any more transitions here to cover that. It's because it's just going to assume that it rejects. But if we're in the even state at the end and we've got a blank, so we've got no more zeros, that's our cue to go back to the beginning and start over again. So I guess I'm going to need another state, and I'm going to leave a little space up here. I need another state here, so if I get a blank, I'm going to do nothing to it. I'm going to move to the left. And now I'm potentially scanning a 0 or an X, most likely an X, because we've just crossed off an X if we got here, or we just crossed off an X if we got here. And we're going to want to move back. So we know that since we're scanning an X, we probably want to move left with X's, but also with zeros. And doing that, we'll skip over all our non-blank symbols. So I'm just anticipating I probably want to go back to the beginning and get started again if I see a blank. So if I see a blank and then move right, because we've been moving left, that will put us back onto the first non-blank symbol. And we should be careful, because the first non-blank symbol, oh, it looks like it should be a 0, so I should be okay there. It should remain a 0. Remember, my plan was the first one should always be a 0. And then if we get the 0, we can go cross it off again, and it's 0. Okay, what the problem is, after that first 0, we would have an X there again. So I do think I need some loops here that allow me to skip over those X's. Same here and over here. This will allow us to skip the X's that we've crossed in our previous loops, so that on this loop we're only crossing every other 0 that hasn't already been crossed. Okay, now all of this is well and good. We're being crossing. We've looped back, but when are we supposed to accept? Okay, now remember I said we're supposed to accept when we get down to exactly 1, 0. And one way that might help us figure this out is what happens if we just have exactly 1, 0. If we have exactly 1, 0, we're going to move to the right here. And then we're going to get to this state, and then we'll be scanning, of course, a blank. So if we do that, we know in this case we need to go to an accept state if we see a blank. And again, I just move right and write a blank because that's my default. It doesn't matter what you do. So we'll go to our accept state in this case, but now let's make sure it will still work in this case here. What would happen here? We'd rewinded ourselves back and we read our first 0, but then we're going to skip over all our X's, and sure enough, there's a blank at the end there that will kick us into the accept state before we get rejected otherwise. So that's great. I think we've got it. And again, maybe I said I was going to do that. Why didn't we loop back earlier? Why didn't we loop back here, or something like just have 2 states The reason is this special check for the accepting condition is we want to always start our journey to the right as though we were going to be crossing off. But if we find no second one to cross off is when we should accept, and that's why we have this special case. So our loop had to be over here in these two states instead. Okay, so this is another language that is not context-free, and I think we did show this was not context-free in an earlier video. So again, this will help us show that this particular language is a language that is not context-free, but is decided by a Turing machine, as have both of our other languages so far. So let's get this started. How are we going to make this one work? So maybe we have 0, 1, 1, 0, hash, 0, 1, 1, 0, same thing. I kind of want to match things up. I got a 0 over here, got a 0 over here. Come over here, I got a 1, got a 1. One of the important things about this one is that we do need to also remember what symbol it is. I got a 1 here, so when I get over here, I make sure it's a 1. If it's not a 1, I should be doing a rejection. So that's maybe the first thing I'm going to think about. I'm going to design my Turing machine a little strategically. You notice I drew this a little bit down lower because I want to have some kind of branch going on at the beginning. When I remember, if I got a 0 and I cross it off, I want to remember it. And if I get a 1 and cross it off, I want to remember that too. So that first state, it looks like, is going to be used to do a branch into two paths. Now these paths are probably going to be the same, and we have this programmer's desire to try and reuse stuff. Well, we can't reuse them just because we've got a rewind state. We need to remember this is the rewind state when I've got a 0, or this is the rewind state when I've got a 1. So we use our states as a special kind of memory. So let's just do one of the paths, maybe the one with the 0 first, and then we will probably be able to mirror it with the other path. So if we've got a 0, we move to the right. Now I want to move to the right on all the symbols, 0s, 1s. What symbol is going to trigger our movement to a new state is when we see that special symbol that we have here, the hash symbol. I'm going to leave it alone when I see it, but I'm going to move to the right because now I know I should be scanning the first symbol on the right hand side of my hash, the beginning of my other W. Now if this is my first path and I had seen a 0, I should be scanning hopefully another 0. If not, I should reject. So if I see another 0, I'll cross it off. And I'll maybe start moving left because it's time to rewind. So I said rewind. What is rewinding going to do? That's going to be okay. If I see a 0, I want to just write a 0 and move left. If I see a 1, I want to write a 1 and move left. If I see an X, I want to write an X and move left. And for that matter, if I see the special symbol hash, I just want to skip it too. This basically skips every single symbol except when it sees a blank. And if it sees a blank and moves to the right, it will be right back where we started at the beginning of our input. Okay, before I do my other branch, I want to just go back to my first branch and inspect to see where I might have to skip some X's that I didn't do when I first thought it out. So on my first step through, I assumed I was scanning that first 0, but remember after the first loop, there might be X's there instead. I want to skip over the X's and then get to the first symbol. Now if it's a 0, okay, I'll cross it off. Then after I've crossed it off, after the symbols I've crossed off while I'm moving to the right, there are only 0s and 1s before I hit the hash. So here I don't think I need the X's in there because I'm going to hit the hash next. Then I hit the hash. Again, here I just assumed the 0 was the first one. If I got a 1, I do want to reject, but if I got an X, no, that's that first X there. I want to skip it. Okay, now when I get, now I maybe see that first 0, so I did see the one that I want. I crossed it off, I rewind, and I'm back. So I think I can do this again with another pair of states down here. This state is going to mirror the one up above there. We'll skip our 0s and our 1s. Then we move to the right when we see our special hash symbol. This next state should skip our x's. And if it sees the 1 that we remembered now, we'll cross it off and we'll start our way back and we'll head to our rewind state, which we can share now because now that we've remembered our 1 and we've used it for what we wanted it to, we can do a shared rewind state. So that will rewind us back to the beginning and get us started again. Again, we already put our little X skipper at there so we can get ready for that next step. And as long as we're going back and forth here, and we cross off 0, 0, 1, 1, and so on, then at the end, how are we going to end up? Well, we might end up with a string that looks something like this. So I think what we want to consider is what happens when we see the special symbol here. I'm going to just leave it as and move to the right. And again, let's consider a very special string. What about this string? Just a hash. Just a hash is an epsilon hash epsilon. That looks like it's in this language. So that should be accepted. So if I just see a hash here and move to the right, there's a temptation to say, oh, let's make it an accept state. But what if it was a hash and a 0? That's an epsilon and then something. We don't want that. So instead, I have to check for the hash, but I also have to check to the right and make sure there's a bucket there or nothing there. So I'm going to go instead, to get to my accept state, you also have to see the empty, or the bucket, the blank. And what we'll notice here is in this case, it won't necessarily be a blank in the first square. It might be X's. So let's not forget to skip some X's as we go. Okay, I think that one finished it off for our WW. And again, now what we're seeing, okay, let's count them out. 1, 2, 3, 4, 5, 6, 7, 8 states that we use for this one. These state machines are getting a little bit complicated. And in terms of the types of languages that Turing machines can handle, these are incredibly simple languages. So if we want to build Turing machines that can compute languages that are way more sophisticated, the number of states we might be drawing are in the thousands, potentially even in the millions. Now remember, a Turing machine is a model of your general purpose computer. So anything that you could compute on your computer, you could compute on a Turing machine. So for instance, there's a Turing machine that plays Spotify. That Turing machine probably has trillions of states. We don't want to draw it. We don't want to write it down. We do want to talk about it. We do want to think about it, maybe formally, so we could prove something about it. So we're going to have other tools than state diagrams to describe our Turing machines. And sure enough, that is something that we're going to look at in a future video. Specifically, we're going to look at using pseudocode to describe how a Turing machine works, now that we're pretty familiar with the kinds of things that a Turing machine can do. All right, thanks a lot for watching, and we'll see you in that next video.